पीएमएमसी एंड मूविंग आयरन कंप्लीट कर चुका है। आज हम डिस्कस करेंगे डायनेमोमीटर। जल्दी से जल्दी सेशन को लाइक कर दो बेटा। नमस्कार दोस्तों, वेलकम टू गेट वाला। तो मैं हूं सतीश कुमार दुर्शेट्टी, फैकल्टी ऑफ मेजरमेंट्स। सब लोग कैसे हो? आज हम लेक्चर नंबर 3 स्टार्ट कर रहे। लास्ट क्लासेस में हमने मेजरिंग इंस्ट्रूमेंट्स में हमने क्या क्या डिस्कस किया, पीएमएमसी डिस्कस किया, मूविंग आयरन डिस्कस किया। तो आज हम डिस्कस करेंगे डायनेमोमीटर एंड इसके बाद हमने करंट ट्रांसफार्मर भी डिस्कस करेंगे, इंस्ट्रूमेंट ट्रांसफार्मर का एक बार था क्वेश्चन। सो टुडे विल डिस्कस डायनेमोमीटर वर्किंग and dynamometer torque expression will discuss. We'll discuss dynamometer working and dynamometer torque expression. And after that we'll go to the instrument transformers. बिकॉज फॉर इलेक्ट्रिकल पीपल वन ऑफ द इंपॉर्टेंट टॉपिक है। इंस्ट्रूमेंट ट्रांसफार्मर्स में मैं पहले डिस्कस करना चाहता हूं करंट ट्रांसफार्मर। करंट ट्रांसफार्मर डिस्कस करना चाहता हूं, उसको हम सीटी बोलते हैं। ओके, चलो स्टार्ट करेंगे डायनेमोमीटर वर्किंग। So let us discuss the dynamometer working. So dynamometer is a combination of actually ये कलेक्टेड स्लाइड से जल्दी से जल्दी ज्वाइन कर दो बेटा। जितने लोग लाइव में हैं प्लीज कंडक्ट इंस्ट्रूमेंट। पॉसिबल नहीं है अल्ताफ, इट्स नॉट पॉसिबल। डोंट आस्क मी बार बार, ओके, एंड डोंट इरिटेट मी। दिस अ मेजरमेंट्स टॉपिक, प्लीज फोकस ऑन द मेजरमेंट्स। मेरे हाथ में नहीं है, डोंट आस्क मी। वी आर नॉट कंडक्टिंग एनी क्रैश कोर्स फॉर इंस्ट्रूमेंटेशन, ओके। ऑलरेडी आई हैव गिवन दिस आंसर इन द लास्ट क्लास। व्हाई यू आर इरिटेटिंग हियर? सॉरी, आई एम सॉरी। देयर इज नो इंस्ट्रूमेंटेशन हियर राइट नाउ। डायनामोमीटर मेजरमेंट्स 8 मार्क्स का वेटेज आएगा इंस्ट्रूमेंटेशन बच्चों के लिए। सो अगर आप मेजरमेंट सुने तो यस आंसर कर दी। सो डायनामोमीटर एज पर द शेड्यूल इट इज नॉट देयर यार, दैट्स व्हाई आई एम टेलिंग। ऑलरेडी आई इन्फॉर्म्ड दैट एज पर द शेड्यूल वी डोंट हैव द इंस्ट्रूमेंटेशन। Hey, don't irritate. One second. First, please make a note of this. चलो, PMMC we have completed. PMMC stands for permanent magnet and moving coil. Here the magnet is permanent and the coil is a moving object. इसमें क्या क्या आएगा आपको? IDC and VDC आएगा. So it is used for the measurement of DC current and DC voltage. Next इसके बाद moving iron है. Moving iron में electromagnet है, moving disk है. So this is for the flux and this is for the deflection. So this is suitable for measurement of DC current and DC voltage and AC current and AC voltage. Now dynamometer. So dynamometer क्या है? Dynamometer is a combination of moving iron, PMMC. That means it is a combination of electromagnet plus moving coil. So it is called EMMC. What we call? We call it as EMMC, electromagnet moving coil type. So please make a note of this. We call it as electromagnet moving coil. Electromagnet moving coil type. Okay, so it is an electromagnet moving coil type. So why it is called electromagnet moving coil? It is taking the feature of electromagnet from the moving iron and it is taking the moving coil feature from the PMMC. Okay, that's why it is called as electromagnet moving coil. Chalo. So let us see the constructional features. It is called electromagnet because electromagnet feature is taken from moving iron. Electromagnet feature is taken from the moving iron and the moving coil feature is taken from the PMMC. Moving coil feature is taken from the PMMC and it is called the transfer type instrument. Why it is called transfer type instrument? The reason is it is tested in the DC. First it will be tested in the DC and it can be calibrated for AC also. Okay, so what are the measurements we can do? We can do the AC current and DC current. We can use the AC voltage and DC voltage and we can use for the AC power and DC power, and preferably it is an average power only. What is the average power? That is the VI cos phi. VI cos phi. So DC power, voltage and current, whereas the AC power, average power, that is a VI cos phi, where cos phi is the power factor. So in another way it is also suitable for the power factor measurement. Okay, but majorly if you see the characteristics of the dynamometer characteristics here as a ammeter. So if it is used for the current measurement, it is called as dynamometer type ammeter. What we call? We call it as dynamometer type ammeter. And if it is used as a voltmeter na, so we call it as dynamometer type voltmeter. Dynamometer voltmeter. Suppose if it is used for the power measurement na, then it is called dynamometer wattmeter. Dynamometer wattmeter. So try to understand dynamometer ammeter, dynamometer voltmeter, dynamometer, wattmeter. So if you see the characteristics of this, dynamometer ammeter, dynamometer type voltmeter, dynamometer type wattmeter. So these are three graphs. This is the dynamometer type ammeter. This is the dynamometer type ammeter. This is the dynamometer type voltmeter. This is the dynamometer type wattmeter. Okay, so if you see the graph of dynamometer type voltmeter ammeter, the graph is non-uniform. Voltmeter graph is also not uniform, but wattmeter graph is uniform. This graph is uniform. So try to understand, this is a non-uniform. The non-uniform scale. It is also non-uniform. It is uniform. Here the deflection, and this is the average power, and this is the deflection and the voltage, the deflection and the current. Okay, Altaf. Now let us see the constructional features. Dynamometer basically works on the concept of mutual inductance. It works on the concept of mutual inductance. Concept of mutual inductance. Mutual inductance is going to present when there are more than two coils. So this is the fixed coil and this is a moving coil. There are two coils. One is a fixed coil, other one is a moving coil. So if you see the constructional features, so this is the basic constructional features of the dynamometer. So in short, I have given, there is a fixed coil 1. So this is a fixed coil. This is a fixed coil 1. This is a fixed coil 2. This is a moving coil. Okay, so generally fixed coil will be thick in size, whereas a moving coil will be thin in size and lengthier. So this is a fixed coil, or we can call it also current coil. This is what we call as current coil. This is what we call as moving coil. This is our phone number. Phone number. Call it. Matlad. So this is what we call as moving coil or voltage coil or potential coil. There are different names. Potential coil. So this is what we call as current coil, which is a fixed coil, and this is a moving coil. So current coil is thick in size and shorter in length, whereas a potential coil thin in size and longer in length. Okay, that's it. Please make a note of these points. Any doubts you can ask me. Altaf, are you there?
Okay.
మాట్లాడు ఫోన్ మాట్లాడడం అయిపోతుంది ఫోన్
Okay.
So here, what is happening? Why it should be thick? Why it should be thick and why it should be shorter? If you see the resistance is equal to rho L by A. The more is the area of cross section, the lesser will be the resistance. The more will be the current. The more will be the current. Okay, keep this in mind. So for that purpose, the area of cross section is wider. Whereas moving coil, resistance should be more so that the voltage is longer. Okay, so it is generated for the voltage of the pressure coil. It is generated for the current passing through the current coil, so that I can get the power V into I. So whenever the current passes now, this fixed coil is divided into two parts. This is a part 1 and this is a part 2. So whenever a current travels, it becomes like a magnet. Why? Because it is electromagnet. So it is an electromagnet. Whenever a current passes through a coil, it acts like a magnet. Remember, both the coils are current coil or pressure coil. Both are air cooled coils. So the losses are less. Remember this point. Okay, the losses are very less. So when a current travels in the fixed coil, those two fixed coils will act like a magnet. Between the two magnets, there is another magnet called moving coil. So it also acts like a magnet. So there is a deflecting force. That force makes this coil to deflect. So how much deflection will be there? That is in relation with this current passing to current coil and this current passing to the pressure coil. So we will take it as I1 and we will take it as I2. Constructional features, if you take, the moving coil cannot be purely inductive. So there will be definitely a resistance. So because of that resistance, what happens now? So there is a possibility of voltage here. Okay, so this pressure coil develops the voltage and the current coils develops the current. So as a result, we are going to get the torque expression. So torque expression, I want to just explain the derivation. See here. So if you see the derivation, we know the power is equal to energy per time, energy is equal to power into time. So power is equal to voltage into current. Power is equal to voltage into current. So this is E1 and I1, this is E2 I2. So the energy supplied to this coil 1, energy supplied to this coil 2. So energy supplied to this coil 1 is this, energy supplied to this coil 2 is this. Okay, so energy supplied to the coil 1, energy supplied to coil 2 this. So what is the energy expression? We know that self inductance is equal to 5 by I, Li is equal to 5, but here Here remember, the change in flux, the EMF is not happening only due to change in inductance. It is also due to change in flux. That's why I am taking d phi by dt, d by dt of this expression if I am taking. And most important thing is between these coils, in this the flux is due to self-inductance, and there is also another flux due to the mutual inductance. So that's why this mutual inductance components I am taking. So the flux is equal to L1 into I1 plus M into I2. So if you take the derivation, you are going to get this expression. Please make a note of this expression. Please try to make a note of these expressions first. All of you noted down? Have you noted it? Can you please respond? जितने लोग लाइव में देख रहे हैं मुझे एक बार कंफर्मेशन कर दीजिए बेटा. जितने लोग लाइव में देख रहे हैं एक बार मुझे कंफर्मेशन कर दीजिए. सात लोग देख रहे हैं एक बार मुझे कंफर्मेशन कर दीजिए. Have you understood the expression for energy or not? देखो बेटा ध्यान से. So this is the energy supplied to the current coil. This is energy supplied to the second coil. Okay. So the total energy, I got it. The total energy is this. Total energy is this. So by solving this total energy, what happens to this energy supplied? This energy will be resulting into the change in incremental energy on the inductors and the mechanical work done. Change in incremental energy, stored energy and the mechanical work done. So if you see this, finally we are going to get the torque expression as Td is equal to I1 I2 dm by d theta. So I told you already, in electrostatic voltmeter, the torque is related to dc by d theta. In moving iron, the torque is related to dl by d theta. And in dynamometer, the torque is related to dm by d theta. So the deflection torque expression is actually this. But if you take the I1 is equal to I2, I can take I square into dm by d theta. Okay, so these are all mathematical derivations. Okay, so here I want to give one clarity once again. Before entering into that, I want to give one clarity. See here. What is that clarity? So if you see the once again measuring instrument, the deflection torque and the controlling torque and the application. Bar I am telling this. So this is the measuring instrument. and this is a deflection torque, is a controlling torque, and this is the application. Measuring instrument, first if I am taking the PMMC, for PMMC, Dyna DC KC theta, application is only DC. And here if I am taking the moving iron, deflection torque is 1 by 2 I square TL by d theta, and this is KC theta. So this is for DC and AC. If I am going for electrostatic voltmeter, so the deflection torque is given as 1 by 2 V square DC by d theta. This is KC theta, and it is also for both DC and AC. And finally, when it comes to the dynamometer, for dynamometer it is I square dm by d theta. So see the difference. For moving iron we got as dl by d theta. For electrostatic voltmeter we got it as dc by d theta. So this is KC theta. It is also DC AC measurements. So please have a note of this. So today's session is entirely related to this. So dynamometer expression is given by I square into dm by d theta. So now based on that we can go for the torque expression here. So if you see the torque expression, but if you see the characteristics here, the deflection torque is given by I square into dm by d theta, controlling torque is given by kc theta. At steady state Td is equal to Tc. So this I square dm by d theta is equal to kc theta. So theta is proportional to I square. So if you see, the characteristics are not linear, non-uniform, and most important thing, it is I square. So it is suitable for both AC and DC. Even a negative ripple also can be detected. For negative ripple also, what happens? There is a deflection. So some students may think how it is happening. So for a positive side, what happens? This magnet will be north pole, south pole. This magnet will be north pole, south pole, and this will be north pole, south pole, and between the north and south there is attraction, there is an attracting force. So for the positive half cycle. But when it happens to the negative half cycle, for a negative half cycle also what happens? For negative half cycle what happens? This polarity gets disturbed. So this north pole, south pole gets disturbed to south to north, and this gets disturbed to south to north, and similarly this also changes to south to north. Again the deflection continues according to the magnitude of the currents. So it is suitable for both AC currents as well as DC currents. So it is suitable for both AC and DC measurements. So that is a point. So now let us see the characteristics. So these are the basic characteristics. Okay, these are the basic characteristics. Make a note of these points. So if you see, suppose how it can be suitable for the power measurement, that is the most important thing. So here I am taking both I1 is equal to I2, that's why I square dm by d theta. So that's why non-uniform, and this is also non-uniform is coming. Okay. So but if you want to go for dynamometer type voltmeter, dynamometer type wattmeter, if you want to go for dynamometer wattmeter, the deflection torque, if you can see, the I1 is a current passing through the current coil, so that I can take it as Im1 sin omega t, whereas I2, the current passing the pressure coil, cannot be exactly same because the pressure coil construction will be entirely different. That's why omega 2 minus phi. So current coil is purely resistive. Sorry, it can be allowing the current perfectly, but if you see the pressure coil current, so there exists a difference. This is the phi. Okay. So now if you see the average torque, I1 I2 dm by d theta. So that means if you see, sorry, this I1 I can take it as Im1 sin omega t integration of 0 to 2 pi 1 by t. Suppose if you want to take the average torque, how to do it? If you want to take the average torque, I can take it as 1 by 2 pi integration of 0 to 2 pi td d theta. So that I can write like 1 by 2 pi integration of 0 to 2 pi. Td is I1 I2 dm by d theta into theta. Here I can take it as 1 by 2 pi integration of 0 to 2 pi. If I am taking this as Im1 sin omega t, and if I am taking this as Im2 sin omega t minus phi into dm by d theta, and this theta I can take it as d omega t. Yes, Ashish, have you noted it? So if you simplify this, what I am going to get, 1 by 2 pi, this is Im1 comes out, Im2 comes out, dm by d theta also comes out, integration of 0 to 2 pi sin omega t into sin omega t minus phi, and dm by d theta you are going to get, sorry, d omega t you are going to get. So this is how the torque expression will be developed. Okay. So now if you simplify this, if you apply the integration, we are going to get cos here also sin omega t minus phi integration, and if you apply the limits, then finally what we are going to get now, we are going to get Td is equal to 1 by 2 pi Im1 by Im2. So this one I am going to get as, just I am going to get as cos phi, going to get as only cos phi into 1 by 2 here. Into make simplification on this, and finally we are going to get this as IPC, VPC cos phi into dm by d theta we are going to get. Final expression. Current passing through the current coil ICC is the final expression we are going to get. Okay, so if you want, you can take this as actually this is current pass in the current coil, this is a current pass in the pressure coil, and finally we can also take this as VPC by RPC into cos phi to dm by d theta. So this I can write it as ICC VPC cos phi 1 by RPC into dm by d theta. So this is a deflection torque. Okay, and the controlling torque I can take Kc into theta. Okay, so at steady state, if you take ICC VPC cos phi into 1 by RPC dm by d theta is equal to Kc into theta. So theta is proportional to VPC ICC cos phi. So this is what we call as theta is proportional to average power. So once again I am repeating, dynamometer ammeter will get the deflection theta is proportional to I square non-uniform scale. Dynamometer voltmeter theta is proportional to V square non-uniform. Dynamometer wattmeter theta is proportional to average power. So this is the uniform scale. That's what we got here. Okay, are you getting, my dear? Ashish, are you there? Got the answer? R is the resistance of the pressure coil. So if you see the dynamometer connections, if you see the dynamometer basic diagram, so this is the current coil. If you see the dynamometer connections, this is a current coil. So I can take this as a load, and here comes the pressure coil, and here comes the resistance. So this is the load. This is a pressure coil resistance. So this is a single phase supply. So now where I can fix this? If I fix here, then it is going to be the main section. So this is what we call as MC connection, dynamometer MC connection. Main side connected. Okay, dynamometer MC connection. It is MC connected, mains connected. Pressure coil can be connected to the main side. This is the main side. So this is a load side. So MC connection. MC connection means pressure coil connected at mains side. So when it is connected at the main side, there is an error. There will be error. Can you tell me what is the error here? Anybody? Can you derive the error here in this connection? Can you derive the error here in this connection, my dear? Please tell me what is the error in this side. I am expecting the answer from you. Why? Because the true power is this. Is a current passing through the load. Is a voltage across the load. And this is a current passing through the load. Okay. Tell me. The same current is traveling here. So this is what is the true power? What is the true power and what is the measurement power? If you see the true power, the true value is VL IL cos phi, and the measurement value is, in addition to this true value, the mains connection is here. It is connected here. So that means there is a possibility of getting this power also. Okay. So the power due to is connected here also now. So what we can take? The current coil also we can take. It includes the true value, the power consumed is only the load side, VL IL cos phi, but the measurement value, what it includes this also now. This is the terminal, right, from here to here. So it includes this. So the measurement value is, in addition to true value, power consumed by the current coil. What is the power consumed by current coil? The resistance of the current coil is RCC. Current passing is ICC. So what I can take, this is the true value, and I can take it as current passing through this I square RCC. Power is equal to I square R. So this is the measurement value. So there exists error. Error is equal to measurement value minus true value. If you see that, that will be error due to okay. So if you want to expect the error to be less, what is the condition? So this I square RCC must be less. You cannot say RCC less, that is a constructional feature. So ICC must be less. ICC must be less means I load must be less. That means it should be suitable for, so MC connection is suits MC connection suits for smaller load currents or high resistive loads. High resistive. Okay, that's the point. Please make a note of this point. Note. In MC connection, the error is due to the current coil, that is square. Chalo, let us go for the other connection. We can also make the connection this side. Okay, can anybody tell me now? Suppose if I have connected this particular pressure coil at this side, then it is what connection? Can anybody reply me here? If the pressure coil is connected, anybody reply me? If the pressure coil is connected at this side, I mean, if the pressure coil is connected at this side, then what it is? Tell me, man. Then what connection it is? See here, that is what we call as LC connection. So what we call this as dynamometer LC connection, load side connection. Dynamometer LC So how it works? Let us see. The current coil, the load, so this is a pressure coil, see here. So this is a current coil, pressure coil, and here resistance. Load. And this time is connected this side. Single phase supply now. Understood? Yeah. If this is a scenario, how to do? So this is the LC connection. LC means load side connected. Load side connected. Who is connected? The pressure coil. So based upon the pressure coil connection only, there will be error. If the pressure coil is connected at the main side, it is called MC connection. If the pressure coil is connected at the load side, it is called LC connection. Now tell me, here also what is the possibility? If you check the true value, again same. You see this the current passing, but here you have to understand this is the current split in two parts. Current passing the pressure coil, and this is a current passing through the load. This is a current, this is a voltage across the load. Okay, so now if I am seeing the true value, that is VL IL cos phi. Okay, the measurement value, if you check now, in addition to the true value, there is an extra. What is that extra power? So that is the power consumed by the pressure coil. The power consumed by the pressure coil. So that is a power consumed by the pressure coil, that we can take it as VPC by RPC. So error is equal to measurement value minus true value. So that is VPC square by, so this is the error. So error has to be less. That means the VPC has to be less. VPC has to be less means the current passing through this pressure coil must be less. Current passing through the pressure coil must be less means current passing through the load must be more. So MC connection suits for dash. MC connection best suits for dash. Can anybody tell me now? Previously we have seen LC connection. Now what happens to the MC connection? Previously we have taken a conclusion, LC connection, sorry, is MC connection and this is a LC connection, load side connected, sorry. This is a LC connection. Now tell me, LC connection is best suits for what? So error कम होना बोले तो V कम होना है, V कम होना बोले तो इधर I कम होना है, I कम होना बोले तो IL ज़्यादा होना है. That means it is suitable for larger load currents, larger load currents. So larger load currents are possible when for small loads. Okay, please make a note. In LC connection, the error is due to which coil? To pressure coil. That is V square by. Please make a note of these points. taken? It's all about the MC connection and LC connection. Chalo. Let us move for the next topic, that is a current transformer. So the next topic that I want to discuss is instrument transformers, one of the important topic for the electrical students. Instrument transformers. Please just go through these slides. See, whenever you want to measure the high voltage or high current, even though PMMC we have range extension, and moving iron also we have range extension, but we cannot use them directly for the high current measurement and high voltage measurement. That's why instrument transformers we are using for the measurement of high voltage and high current. So they are suitable for measurement of high voltage. They are suitable for measurement of high voltage, that means in the range of kilovolts, and high currents. Okay, so it is a combination of two things. Instrument transformer is a combination of two things. One is a transformer, other one is the instrument. Transformer, other one is the instrument. So what is the purpose of transformer? The transformer is used to scale down, whereas the instrument is used to measure. Okay, so the transformer is used to scale down the voltage or the current, and whereas the instrument is used to measure. So for example, if you take the current transformer, CT stands for current transformer. Current transformer will convert the 100 amperes to 5 amperes. Next, PT, it is also called as potential transformer. It is suitable to convert 110 kilovolts to 110 volts. 110 kilovolts to 110 volts. Is it clear? 110 kilovolts to 110 volts. Yeah. After that, we will go for the measurement. After that, we are going for the measuring instrument. So first, let us talk about the constructional features. Okay. Before entering, I think all of you know the fundamental basics of a transformer. The basics of a transformer is like this. V is proportional to N. The V is proportional to N. Yes or not? So the basic relation is this. For any transformer, V is proportional to N, whereas the current is inversely proportional to N. So the relation is V1 by V2 is equal to N1 by N2 or I2 by I1. So V is proportional to N, V1 by V2 is equal to N1 by N2. So if you want to scale down the voltage, what is the basic condition? So I want to scale down the voltage, that means V2 should be lesser than the V1. So what I can take V1 into N2 by N1. So V2 should be lesser. So what should I do? So if V1 is more, V2 should be less. That means by reducing the number of turns. So if N1 and N2, if you check, N2 should be very, very less. N1 should be more. So that's why N2 should be less. Okay, N1 should be more. So N2 should be less means the least value of turn, at least one turn may be there. So if I am taking N2 as 1, what should be the number of turns at the primary side? So if you want to scale down the voltage from a higher value to the lower value, what is the condition? At the secondary side, the number of turns must be as least as possible, that is equal to 1. So at the secondary side, the number of turns is equal to 1, then what is the primary side turns? So that is only the question. So primary side turns, if you know, by designing the turns at the primary side, you can scale down the voltage from V1 to V2. So if I am taking V1 by V2 is equal to N1 by N2, N2 is equal to 1, then N1 will be mostly, this is the expression. N1 is, okay. Suppose if I want to convert 110 kilovolts to 110 kilovolts to, suppose if I want to convert 110 kilovolts to 110 volts, if I want to convert this 110 kilovolts to 110 volts, then what happens? So V2 is equal to 110 volts, V1 is equal to 110 kilovolts, and N2 is equal to 1, N1 we want to know. So N1 answer we are going to get as 1000. We are going to get the N1 answer as how much? 1000. Is it clear? So let us go for the next. The same similarity if you go for the current transformer. I is inversely proportional to N, I1 by I2 is equal to N2 by N1. So I1 by I2, so current is I1 by I2, 100 amperes by 5 amperes, N2 by N1. So what is the N2? N2 will be 20. number of turns in the secondary side will be how much? 20. Why? Current should be scaled down. Current should be scaled down means the secondary current must be lesser than the primary current. So current should be scaled down means that number of turns I is inversely proportional to N means the number of turns must be more. So if you take the least turns at the primary side as 1, N2 will be 20. So by choosing the current N2 is equal to 20, by choosing the turns at N1 primary side as 1 and at the secondary side as 20, the current 100 amperes 5 amperes conversion can be possible. So 100 amperes current is possible to 5 amperes. So this is a concept behind the potential transformer. This is a concept behind the current transformer. So we are using the same concept for the construction. So check now. So this is the potential transformer basic diagram. The potential transformer basic diagram. In potential transformer, we are using the number of turns at the primary side as 1000, number of turns at the secondary side as 1. So the V1 is 110 kilovolts. So this is a V1 and this is the V2. Okay. So 110 kilovolts is converted to 110 volts. 110 kilovolts is converted to 110. So this is the diagram of potential transformer. And if you see the potential transformer is called parallel transformer. It is not coming in series. And the secondary instrument here that we can keep here, it can be either it can be a voltmeter, it can be a voltmeter, it can be a voltmeter. Voltmeter means I can use the PMMC or moving iron, whatever it may be. Okay. You cannot use perfectly PMMC, AC voltmeter you can use, moving iron type, or you can use the pressure coil of wattmeter you can use, or you can use the pressure coil of energy meter. Pressure coil of energy. Okay, so this is the basic concept of the potential transformer. If you see the potential transformer slides, what are the features of the potential transformer? Potential transformer basically used to convert 110 kilovolts to 110 volts. The secondary voltage will be in the range of how much? The secondary voltage in the range of 110 volts. So basic feature is number of turns in the primary side will be more than the number of turns in the secondary. N1 is greater than N2. It is called as parallel. Why? Because potential transformer comes across to supply. It comes across to supply. Please remember this point. Next, secondary instrument transformer voltage, it can be voltmeter, it can be pressure coil of the wattmeter, pressure coil of the energy meter. And next, let us go for the current transformer diagram. If you see the current transformer, this is what our topic actually. Yes, Ankur, क्या चाहिए? Ankur, tell me. क्या चाहिए? What happened? In current transformer, if you see the current transformer is again a combination of a transformer and an instrument. Here, the transformer comes in series to the current. So this is a higher current, which is generally 100 amperes current. This has to be converted to 5 amperes. This has to be converted to 5 amperes. So what is the logic? The number of turns at the secondary side must be greater. So I am choosing the number of turns at the secondary side as 20 and the least here is 1. So these are 1 ton. So these are 20. So that I am going to get this I2 as lesser. Okay. And what are the basic features here? This current transformer comes in series. Current transformer comes in series to this. Okay. And the meter that we are connecting is a meter, or it can be a current coil of the wattmeter, or it can be a current coil of the energy meter. Yes. What is your problem, Ankur? Yes. So it can be a meter. It can be a meter, or it can be current coil of wattmeter, or it is current coil of energy meter. Okay, so please make a note of these points. Chalo. So if you see the features of the current transformer, the rating is 100 amperes to 5 amperes majorly. So the secondary current rating is 5 amperes. Okay, and it is called series transformer because the current transformer comes in series. CT in series. CT in series to supply. Okay. What's the doubt? Any doubt? Yes, Ankur, what is the doubt? चलो. So now majorly हमारा questions gate में current transfer पर आ चुका है अब तक. तो current transformer का basic formulas क्या होता है? What is the ratio conformation factor? Okay. What is the turns ratio, nominal ratio? Okay. What is the ratio error? What is the phase error? इसके ऊपर क्वेश्चंस बहुत सारा आने के चांसेस है. सो इसके पहले आपको ट्रांसफार्मर का बेसिक डायग्राम, ट्रांसफार्मर में बेसिक कंपोनेंट्स क्या क्या रहता है उसके बारे में पढ़ेंगे. देन फेजर डायग्राम एक बार मैं एक्सप्लेन करूंगा. ओके, रेडीमेड स्लाइड्स है, वो स्लाइड से मैं फेजर डायग्राम आपको एक्सप्लेन करूंगा क्योंकि घंटे में 1 घंटा में आप रिजर्व करना बहुत दिक्कत है. सो आई वांट टू फोकस ऑन द मोर कॉन्सेप्ट्स. चलो लेट अस गो फॉर द बेसिक डेफिनेशंस. If you see the basic definition of the current transformer, first one is the turns ratio. First one is the turns ratio, N. Okay, so this turns ratio N, what is turns ratio N? That is a transformer turns ratio. It is for potential transformer, if you take, that will be Vp by Vs, N1 by N2. Always remember the turns ratio must be greater than 1. So primary to secondary, I am taking Vp by Vs turns ratio, and here Ip by Is, so N2 by N1. So for potential transformer, if you take, as the number of turns at the primary side is more than the number of turns at the secondary side, obviously voltage at the primary side and voltage at the secondary side comparatively Vs will be less. Similarly, for CT, if you check, current at the primary side will be more, current at the secondary side is less. So Is is less than I1, so number of turns at the primary side is less, number of turns at the secondary side will be more. So N will be greater than 1 in all the cases. So for potential transformer, the turns ratio is N1 by N2. For current transformer, the turns ratio is N2 by N1. Chalo. Let us go for the next one, transformation ratio. Let us go for the next one, transformation ratio. So transformation ratio, I can take it as primary phasor to secondary phasor. That is Ip by Is. This is very, very important. Why? Because in question solving, there are two ratios. One is a nominal ratio, other one is a transformation ratio. Nominal ratio is given by the rating of the manufacturer, whereas the transformation ratio is given by the phasor diagram. So from the phasor we have to take. From the phasor diagram, I can get the true value, primary phasor to secondary phasor, Ip by Is. Okay, nominal ratio. So this is a nominal ratio, Kn. So rated primary by rated secondary. So this is from the industry rating, so I can take it as Ip by Is. Ip by Is. Chalo. Next, ratio conformation factor, RCF. What is the ratio conformation factor? That is a phasor ratio by nominal ratio, R by Kn. So this R by Kn is equal to 1 for ideal cases. Okay, but practically speaking, the R will be greater than 1. Why? I will tell you that. R will be greater than 1. We are going to derive that. So Why? Because when you derive the expression for the R phasor diagram, IP by IS, so IP is equal to N into IS plus I naught of something will come. So because of that, this extra term will come. So R will be greater than 1 always. Okay. So if I want, I will derive that, but first of all you can write IP by IS, which is I naught plus N into IS sine of alpha plus delta, that we are going to derive next. Okay, but obviously R will be greater than 1 in ideal cases. R will be greater than 1, so definitely we have to check now. Ratio error will be error, measurement value minus true value. So let us go with the phasor diagram first. Before phasor, let us take circuit diagram. So this is a circuit of the current transformer. The circuit of the current transformer. एक बार please note down the current circuit of the CT. All of you please make a note of this current transformer circuit once. Yeah, so this is a current transformer circuit. In current transformer circuit, if you see the number of turns at the primary side and the number of turns at the secondary side, if you compare, number of turns at the primary side will be less, number of turns at the secondary side will be more. So this is the basic transformer diagram. This is a primary side winding LP and the primary side winding resistance RP. So the primary current IP is divided into two slots, that is I0 and NIS. So first of all, let us go step by step. This is a primary side number of turns 1 and the secondary side number of turns is N2. Okay, so the primary side voltage is VP and the voltage here is EP. So the secondary side, if you take secondary side winding resistance and inductance, if you check, and this is the terminal is a terminal load, LE and RE. And most important point you have to understand here is the components. So this is the primary side component IP, primary current. The primary current is split into two parts here. One is the I0 and other one NIS, and I0 is called as no load component, and the secondary side current is IS, and this is the reflected current of the secondary at the primary side. As per your transformer subject, you can go through in your transformer वरुण सर का machines class पे आप देख सकते हैं, तो वहां से आपका ट्रांसफार्मर का कॉन्सेप्ट ले सकते हैं. So this is N into IS. So this I0 is the no load component, is again split into two parts. One is the magnetizing component, which is responsible for the magnetizing flux, which is a basic thing for the flux generation. And next comes the IC, this is a core loss component. So if you see this I0 is the resultant of IC square and IM square, core loss component and the magnetizing component, that is the no load component. And the secondary side voltage, this is the secondary number of turns, that is ES, and this ES is split into IS into ZS plus VS. So this is the ZS and this is the VS. So this ES must be greater than VS. ES is always greater than VS. Okay. So if you check now, ES is equal to IS into ZS plus VS. So ES is containing the secondary side component. This is the terminal component. If suppose the secondary side winding is purely resistive, then this inductive components will be 0. Okay. So that's what I have mentioned. Now let us take the components information first. So I am giving the components information. IP is the primary current, IS is a secondary current, NIS is the secondary current reflected at the primary side, I0 is the no load current. I0 is again split into two parts. One is the IC, other one is the IM, core loss component, which is due to iron losses. Other one is the IM, magnetizing component, which is responsible for phi m. So if you see the phasor diagram of this IC and IM, so first comes the IM. So this is the phi m, which is due to the IM. Okay, next comes the IC. So this angle must be 90 degrees. Okay, the resultant of these two, is this is the I0. I0 is equal to square root of IC square plus IM square. Okay, so that's why I take the resultant component I0. Make a note of these points. And your secondary voltage comes here. So if you take this angle, this particular angle, that is the alpha we can take. So if you take the tan alpha here, tan alpha is equal to IC by IM. So from this we can get the alpha. Next, I am taking this as a secondary. So this is the ES. So here comes the ES, here comes the IS. So this angle is delta. Dear students, try to understand, this VS is the voltage at the terminal side, and the angle between the IS and the ES is always delta. Suppose if it is a purely resistive load at the secondary side, we don't have any inductance, then what happens? This VS will be in phase with the ES, then IS will be in phase with the ES, the delta will be 0. And this IS reflected component, if you take this, so this is the NIS. Understood? So this is what we call as delta. This is what we call as delta. Now let us see the phasor diagram. This is the phasor diagram, complete phasor diagram. Chala time undi Nisha. This is the complete phasor diagram. Please make a note of this phasor diagram. తీసుకెళ్తా పెట్టు పెట్టేసి ఇప్పుడు నేను 9:50కి వెళ్ళాలి. So if you see this phasor diagram, the alpha represents the angle between the IC and IM, the delta represents the angle between the ES and IS, and if I extend this IS, I am going to get NIS. I0 is a resultant component of IC and IM, but I want expressions, that's why I have extended this NIS component towards up, so that I have taken the other components, cos component and the sine component. If you check here, see here, 1 second. So this is my IM, this is my IC. The resultant of this IM and IC is the I0. So this I0 is equal to root over IC square plus IM square. And now if you check this alpha, so tan alpha is equal to IC by IM, alpha is equal to tan inverse of IC by IM. And the secondary side, this is ES. Secondary side, this is the ES, and the VS will be lesser than the ES, and the IS will be lagging by delta. The reflected component of the secondary and the primary side is NIS. So if you extend this IS to the secondary, this is NIS. Okay, so this is NIS, and now if I am taking the resultant of this as a I0, so this will be the I0. And now if you drag this, so now this will be OBC triangle. This will be completely OBC triangle. So I can take this now OB as OA plus AB. That's what I have written here. So from the triangle, if you check now, this is 90 degrees. So please be careful. This is alpha, this is delta, and the angle between the primary component and the secondary component is phi. That is always the angle of power factor, phase angle phi. IP and IS के बीच में रहता है. Okay, so now if you see this, this is 90 degrees, this is alpha, this is delta, and this is what? That's what the most important point. So if you take now, that is 90 minus alpha plus delta, this particular yellow color. So this yellow color and this yellow color both are same. Try to observe this. 90 minus alpha plus delta. So now this particular piece is I0, this particular piece is I0. So it forms like a parallelogram. just use a parallelogram. So this is I0, this is I0. So this angle is 90 minus alpha plus delta. So sine of 90 minus alpha plus delta, if I am taking opposite side by hypotenuse, BC by AC, cos of 90 minus alpha plus delta, if I am taking AB by AC. So this AC is I0. So from this what I can get, the BC is equal to I0 sine of 90 minus alpha plus delta, that is cos. So now I will start the derivation of this particular phase error. If you see this one, alpha is equal to tan inverse of IC by IM. So BC component, AB component we got. Tan phi from the phasor, if you see the tan phi is equal to BC by tan phi, if you check BC by OB. But OB is nothing but OA plus AB. Okay, OA plus AB. So BC is I0 cos of alpha plus delta. What is OA? OA is NIS. AB is I0 sine of alpha plus delta. For smaller angles, you can check here. This is NIS. N will be the nominal ratio. Generally, it will be the more big number. Why? Because when you are taking N1 by N2, N2 by N1 for current transformer, N2 by N1 will be very, very larger. So NIS will be very, very larger than this. Approximately, we can neglect this sign term. So finally, we got tan phi expression. For smaller angles, tan phi is equal to phi I0 cos of alpha plus delta into NIS. This will be in radians. If you want to convert into degrees, you have to multiply with 180 by pi. So we got finally phi. What is this phi? This phi is the angle between the primary current and the secondary reflected component. Okay. That is most important question with respect to your final examinations, and also for your gate examination point of view. Please make note of these points. So we have to remember the phi. Once done, we will start the PYQs. Okay. So we got the tan phi. Phi is equal to I0 cos of alpha plus delta. Similarly, if you go for the ratio error, so how the ratio error is corrected, this is the OC square, OB square plus BC square. If you go all the simplification, this is all not necessary. If you want, I will give the slides. And finally, what we are going to get, the IP expression. IP expression, we are getting NIS I0 sine of alpha plus delta. Okay. So this expression. Please note down. So the transformation ratio means phasor primary to phasor secondary. So IP by IS. So IP is equal to N into IS. N into IS plus I naught of sine of alpha plus delta into IS. So percentage of ratio I can take it as Kn minus R by R into 100. Okay. So obviously this, if you check the R will be greater than N. See, NIS by IS. R is equal to IP by S. How to remember this? I will tell you the technique. R is equal to IP by IS. Phasor primary to phasor secondary. So phasor primary is nothing but N into IS plus extra term I naught sine of alpha plus delta. Okay, IP generally it's NIS, but we are getting an extra term I naught sine of alpha plus delta. IS gets cancelled. Okay, chalo. Let us go with a question. So these are the gate examination most important points, R and phi. For examination point of view, gate examination point of view, these are the important formulas. IP by IS, where IP is equal to N into IS plus I naught of expression. Chalo, let us go with a question. Try to answer this question. Gate 2023 में 2003 का क्वेश्चन है. A 500 amperes by 5 amperes 50 Hz current transformer has a bar primary. The secondary turn burden is a pure resistance of 1 ohm and it draws a current of 5 amperes. If the magnetizing core requires 250 ampere turns, find the percentage of ratio error. So I have given all the data. First let us take the data first. 500 amperes by 5 amperes current transformer. So secondary current is 5 amperes. Bar primary, number of turns in the primary is 1. The secondary burden is a pure resistance of 1 ohm. The secondary burden is a pure resistance of 1 ohm. So secondary burden is pure resistance 1 ohm. So R is 1 ohm. It draws a current of 5 amperes. So we can find out the small n. Small n is equal to N2 by N1, which is I1 by I2. 500 by 5, we got 100. And he has given the magnetizing core requires 250 ampere turns. Magnetizing is at the primary side. So this is 250 ampere turn. That means it is a product of magnetizing current and number of turns in the primary. So number of turns in the primary is 1 turn, IM magnetizing. So from this we got the IM. In the question he has not given any information of IC. So IC is equal to 0. So I naught is equal to root over IC square plus IM square. So I naught is equal to IM, magnetizing component. And remember, the secondary side is a purely resistive. When the secondary side is purely resistive, what happens? The phasor diagram, you can check the phasor diagram here. You can see the phasor diagram here. So this is our IM, because of this is our IM, and this is our IC. And the resultant of this is our I naught. I naught is equal to square root of IC square plus IM square. And this is our ES. This is our ES. As there is purely resistive burden, this will be VS. Previously the VS was having the angle delta, but there is no angle here. So alpha we got, but the delta is equal to 0. Remember this point. Alpha is equal to tan inverse of IC by IM. IC by IM. But in this problem, IC is equal to 0, so alpha is also 0. If IC is equal to 0, then what happens to this I0? I0 is equal to square root of, so this entire diagram will change. So this I0 should come as like this. I0 should come as root over IC square plus IM square. But here IC is equal to 0. So I0 will be equal to IM. So this itself I0. And this is our secondary component. This is our ES. And this is our VS. This is our IS. Okay. And next, if I am taking NIS, so this is our NIS. NIS comes in the opposite. Try to understand the phases. So then where is the IP? IP is a resultant of these two, na? I0 square plus NIS square. So IP comes here. That's what we have drawn. Okay. So IP you can find it out. So how to find IP? IP is equal to square root of I0 square plus. So this is our mathematical analysis. It's a purely resistive, then this is the diagram. Okay. So now I can find out these expressions. R is equal to IP by IS. IP is equal to NIS plus I0 sine of alpha plus delta. So we got these expressions. From the phasor we have to take, remember this point. From the phasor we have to take. That's why from the phasor we have to take, we got this. Okay, that's it. So these are some model questions, my dear. Okay, take this question as assignment. Try to sort out. Take this question as assignment and try to sort out. That's it. You please take this question as assignment. Okay, you try to solve this question as assignment. Enough for today.